All right, well, that was a crazy jump. This is what we're going to be talking about in this video. When an object flies through the air with some sort of horizontal motion in addition to the vertical motions that we've been talking about in class. And in this case, we're going to focus on objects that are initially moving horizontally as they leave some sort of surface and again enter into free fall. To better understand what was going on, we're going to look at a simpler situation where a ball has been launched horizontally and it moves through the air. This photo is taken using a strobe light, meaning that a light flashes at a regular rate, and every time it flashes, a picture of the ball is captured. And so you can see how the path that the ball travels is not a straight line, it is a curve. And in fact, this is a parabola. It's a quadratic relationship that, that we see for a trajectory as the ball moves through the air. If we add into our picture another ball that is dropped at the exact same moment that the first ball was launched, we can see that their vertical motions are the same. They actually fall together as time goes on. What that tells us about the white ball's motion is that the horizontal and the vertical motions are independent of each other. The horizontal speed that the white ball is given does not affect the rate at which it falls. The rate at which it falls is entirely dependent on gravity. That's going to be very useful as we work through our problems, because everything we've learned about an object that's dropping can now be applied to something that is also launched horizontally. In the horizontal direction, there is no force acting on the ball once it's released. And so that means there's no change to the motion of the ball in that direction. Its motion is only changed vertically, not horizontally. And these blue lines help us see that the ball does maintain a constant speed in the horizontal direction. You can see that the distance between the balls in just the horizontal direction stays consistent. And so there's no forward push or backward push on the ball. The acceleration is going to be 0 in that direction. Remember that number, we're going to be using it in our problems. So let's take a look at a situation and kind of see how we would apply these ideas. If a ball is launched horizontally at 20 meters per second from a height of 45 meters, we should be able to find the time in the air. Even though it's traveling really fast, 20 meters per second is like 45 miles per hour, that part of its motion does not affect the fall as it comes to the ground. That's only determined by the height of 45 meters, which is also a really big number, by the way. Since the horizontal and the vertical motions are independent of each other, and there's no upward motion or downward motion to start, we can just sort of pretend like the ball was dropped and temporarily ignore the fact that it's moving horizontally. So we're just going to use the vertical motion to find the time that it's in the air. We're going to start with our formula that involves distance, because we do know a vertical distance, 45 meters. And so this is going to be a useful relationship for us to use. Now, even though the problem has this 20 meters per second in it, and it seems as though that should be our initial velocity, that's a horizontal value. And we are just going to focus right now on the vertical part of the motion. And so we'll put 0 in for that v sub 0. We'll also put in negative 45 in for the displacement, because the ball is ending up 45 meters below where it started. Again, we're just focusing on the up and down part of the motion, the vertical motion. And in that direction, gravity affects things. And so we'll use the acceleration of negative 10 meters per second squared. This comes out to be 3 seconds. By the way, I picked nice numbers for this video. Things might not work out so great on practice problems. So it takes 3 seconds for this ball to hit the ground from this height of 45 meters. As it's doing that, it is also moving horizontally. And so we could add a little bit more to the question, and we could find out how far it moves horizontally, completely independent of what it did vertically, except that the time is the same for both parts of the motion. So we'll use the same equation that we did before, except that we'll use our acceleration as 0, because we're now switching to horizontal values instead of dealing with the vertical ones. We're looking for the delta x here. We're looking for how far it goes. We're putting in now the initial velocity because the 20 meters per second is the speed it was traveling horizontally. And we'll reuse that number that we just calculated, the 3 seconds of time. And again, in this part of the problem, our acceleration is 0 because horizontally there's no forces acting once the ball is in the air, and so the acceleration would also be 0. Now, if you're looking at this slide and you're thinking, wow, that's kind of confusing. How do you know when to use what numbers? How can you keep it straight? Well, let's look at another example, and this time we'll try to organize things right from the start and give you a strategy that you can use to handle these sorts of problems. A chart is going to be really useful here. I can use one side of the chart for my horizontal numbers, one side for my vertical. It'll keep everything separate. I won't have the tendency to sort of put the wrong numbers in, put horizontal numbers in with vertical numbers into a single equation. So here's the question we're going to try to solve. It's kind of related to the video we watched at the beginning. So we've got a stunt that's going on, an 80-meter tall cliff, and the car drives off it, initially moving horizontally. That's our focus in this video, is just horizontal motion to start. And what we find is that the car lands 140 meters from the base of the cliff. So that's a horizontal distance that we know. We also know a vertical distance, how tall the cliff is. From all of this, we can actually figure out how fast the car was traveling when it left the cliff. So let's get organized. We're going to have horizontal numbers separated from vertical numbers. Keep them separated. The thing we're looking for is the horizontal speed. So we'll start with that. That's our unknown. What else do we know in the horizontal direction? Well, again, we know how far it travels horizontally. There's 2 distances in the problem. 80 meters tall is a vertical distance. 140 meters from the base, that's the distance that it traveled horizontally. So I'm going to put that over here. And then one other sort of hidden piece of information is that in the horizontal direction, there's nothing pushing on the car once it leaves the cliff. It doesn't matter if the engine's going. If it doesn't have something to grab onto, that's not going to help the car move forward or backwards. So there's no horizontal force, so there's no horizontal acceleration. All right, let's take a look at the vertical information. Again, we know the height of the cliff. So we know that that's how far the car is gonna travel downward. So we're gonna put that in as a negative 80 meters. I've switched to delta y here. That's just a habit that I've gotten into because I tend to, kind of mix up what's in the x direction, what's in the y direction. So these are just all things that I do to help myself keep things organized in my head. Now, what else I know vertically is that the car was not moving vertically to start. It didn't launch upwards or downwards. It just was moving horizontally as it first left the cliff, that initial moment. And so on this side of the chart, I'm going to say that v sub 0 is 0. Again, that could get confusing. You got v sub 0 on both sides of the chart. That's why you use the chart to separate what's the horizontal motion and what's the vertical motion, knowing that they're independent of each other. And of course, the other thing we always know vertically when something's in the air is that the acceleration is due to gravity, and so it's negative 10 meters per second squared. All right, so how are we going to approach this problem? We are looking for how fast it's going. That's a horizontal number, but there's just not a lot of information over there. I would really like to know a time in order to figure out what that v sub 0 is. And that's exactly what we're going to do. We're going to use the vertical information to find how much time it takes for the car to hit the ground, how much time it takes to drop. And so we're going to answer this question like we've done other dropping problems. We're going to start with our distance formula. Again, I switched to a delta y instead of a delta x to keep myself organized. Over here on the vertical side, my v sub 0 is 0. My fall is 80 meters, and it's downward, so I'm putting that in as a negative 80. And gravity points downwards as well, so I'm putting that in as a negative 10. And when you go through and you solve this, again, I gave myself nice numbers here, so time ends up being 4 seconds. Now that's not my final answer, but it's going to help me figure out how fast the car was initially moving. I'm going to use this over in the other side of my chart. Time is the one thing in this problem that doesn't have a direction to it. It's a scalar. And so it can be used in both the horizontal and the vertical directions. We're going to start with that same basic formula, our distance formula, because we do know some information about distance, 140 meters. I also know that the acceleration is 0, so that's going to simplify my calculations a little bit. And I'm going to use that t value that I just calculated and plug that into the formula as well. And now the only thing I don't know is my speed. The initial speed of the car when it left the cliff was then 35 meters per second.